For the last 5 years, transformers have been the undisputed engine behind large language models. And tech companies are in an arms race to scale them up with ever more data and parameters. A small research lab from Singapore called Sapient Intelligence is questioning that obsession for scale. Their newest model, called Hierarchical Reasoning Model, or HRM, is unexpectedly small and efficient. 27 million parameters, 1,000 training data points, and no pretraining. Yet, the model shows up on the notoriously difficult benchmark ARC-AGI alongside models from OpenAI and Anthropic. This positioning earned Sapient Intelligence a lot of buzz online, but also backlash. Beyond the hype, the paper does raise interesting questions, first about the future of AI, but also meta questions about what trustworthy research looks like. Now, I tend to be a negative Nancy, so to balance me out, I invited my friend Yacine, who is a neuroscience researcher and will walk us through the HRM architecture and its connection to the human brain. You'll find our reading lists and the visuals we use for this video on Patreon for free. With that, let's get started. The HRM model proposes significant architectural changes to the transformer model. But what's wrong with the vanilla transformer model? It turns out there are certain algorithms it simply cannot implement.
Take Sudoku, for instance. The task is to fill in a 9x9 grid so that every row, column, and 3x3 subgrid contains the digits 1 through 9 exactly once. Solving it requires backtracking search. We make a move and check the constraints. If this partial grid is valid, we continue down this path. And otherwise, when we hit a dead end, we backtrack and try another branch. This naturally unfolds as a tree. Crucially, each node in this tree depends on its parent. Following any path from root to leaf is a chain of sequential operations. Transformers, however, can only represent the chain of limited depth. Conceptually, a transformer lays out its computations in 2 dimensions. It applies a fixed stack of T layers sequentially, and within each layer, it processes all N tokens in parallel. This parallelism is powerful, but it doesn't help with problems that require strictly sequential reasoning. Each computational node in the path must happen on its own layer, since it cannot be computed in parallel with its parent. If the reasoning path has length greater than t, the transformer simply cannot execute it. This impedes the transformer from being Turing complete. What's missing is recurrence, the ability to unfold computations over time for as many steps as needed. Now, to be fair, today's transformer-based LLMs do exhibit a form of recurrence. They're auto-regressive. Each new token is generated by conditioning on all the previous ones. Researchers recognize that this looping behavior could be harnessed as a proxy for sequential reasoning. That's the idea behind chain of thought. The model writes out intermediate steps as text, using tokens as a kind of scratchpad before producing the final answer. But this comes at a cost. It slows down inference and uses up GPU cycles for tokens that a lot of LLM providers hide anyway. HRM takes a different approach. It moves the scratchpad inside the model. The loop, or recurrence, is no longer externalized in the output tokens. It's built into the model itself in latent space.
And now I'll hand it over to Yacine to walk us through the architecture of the HRM model. But I'll make sure to chime in with my standard cynical takes.
Hello, I'm Yacine. I'm a researcher and machine learning practitioner, and I'm going to show you what this architecture is about. I'm kind of in the positive side on this one. I really like it, even though some part of the architecture might be of debatable usefulness. So let's dive into it. So here is the full architecture. There's a lot of stuff. I'm going to show you a sneak peek of the end result, and then we're going to deconstruct it and reconstruct it back with all of the idea one after the other. So take a good look at this and forget it, because now we're going to go back to the basic and build up to it. So if we start with the basic setup, we have this a very bare bone architecture where we have the input on the left and then the output on the right. And in between, it's our prediction of what the solution to this given puzzle is. And in between these two, this is where the actual stuff happened. You have the embedding layers over here, which will create an embedding based on the input grid so that it enter our model, which will be an encoder only transformer model of 27 million parameter. And after this model is done doing its stuff, it will hit the linear head that will then create the required output. The training details are normal for this type of model, so use rotational positional encoding over there, add them as an optimizer. Nothing outlandish over here. And we're using an encoder only architecture because we're not dealing with a language model here. So it doesn't have to be a GPT decoder only architecture. It is autoregressive. There's no mega pre-training that it's done. It's just an encoder only model that will take all the input at the same time and then output the whole grid that we need to output. So this is all good, but usually there's a big issue with these type of architecture, which, as Julia explained previously, they are inherently fixed depth. So what we want is something that is a bit more flexible in order to solve puzzles that need backtracking. So let's change the fixed depth architecture without blowing up the number of parameters. So the best way to have much more depth without changing number of parameter is to have what we call a recurrence. You can have multiple sorts of recurrence. Here we're talking about latent recurrence. So the output of the whole model will then be fed to the input, and then you will be able to process it again and again without changing the number of parameters. So this is not a new idea. It dates back from the universal transformer in 2019, which looked like this. It's a bit more complicated because you have the decoder block on the right and then the encoder block on the left. And in our case, we're just dealing with this. And if you see over here, we are recurring into this model for t-step. And after the t-step, we're doing the output. So this is all good, but there's a better way to view this, which is unrolled through time, where each of the t-step is now one view of the model, but at a time step. So if we choose t to be 4, then we will have a view like this. So all of these model will have a shared parameter space, and the input of this one is directly the embeddings. The input of this one will be the output of the previous model, and so on and so forth. So this type of architecture is great. However, as the time step goes bigger and bigger, they usually cannot run for too many steps before it gets lost. So there's an easy fix for this though. The way to palliate this is to have the input re-injected back at each of the recurring step, so as to ground every step of the model with the actual input that it should be working on. There's many names for this type of strategy, but one of them is called recurrent network with recall. So the other argued here that there was still some improvement that could be made to the architecture by taking inspiration from how the mice brain work, especially in their theta gamma coupling in the hippocampal area. So we're gonna take a look at this. The actual neuroscientific element, which I'm very excited about, from this paper come from another one, which is called theta gamma coupling increase during the learning of item context association. I'm not going to go through the whole thing, but the idea is that you have a rat that is within the context, and you need to make a decision about which thing to forage in. And then the context switch, so the room is different, and you need to think again here. And the trick of the game is that the item switch bucket in the different contexts. The interesting bit is this rat is not just a free-form rat. He has a recording wire straight into their brain, and you're able to record specific band in their brain. And the phase frequency that are over here, so the theta band, is coupling with the amplitude of another band, which is the low gamma band over here. And this coupling happened because the population of neurons that are firing in a theta waveform in the population that are in a low gamma frequency are doing it at the same time, so they're working together in some way. That's the idea. So there's a high frequency component and a low frequency one. The theta and the gamma here don't mean much because, as you can see, they don't follow it in the paper. It's more the global idea of having a module that is working at the high frequency and another one that is working at the lower frequency that is aggregating the information of a lower level component. So if we were to look at the change now, it looks like this. So the only thing that changed is here. Now we have this H encoder model that is above what we had before, and it's this one that is actually outputting a state that will go into the linear head. In actuality, we still have a 27 million parameter model. It's just that it's split into two identical models. So these two models are working at different frequency, and it looks like this. So if we follow the input, you have the input that goes into the L model, and then the L model has some state that gets fed to it, and it also receives a state from the H model. So with these three things, it will then process it and try to make an output out of it. And then this output will feed back on itself for one cycle, and then it will stop after T cycle and feed it back to the H model. This is the only time that it feeds back to it after it's done iterating on itself for T time. The H model will look at it, and then it will feed it back into the L model again for another cycle. And it will do this for N cycles, so N iteration. And if you look here, this model doesn't see the input, it just see the output of the L model. And after N times T iteration, the two model will just output their final state. So the L model will output its state here, the H model will output its state here, and it's this H model state, the final one, that will go into the linear head, which will then create our Y hat, which is our prediction at the end. So in a nutshell, this is the basic structure of the hierarchical component. Look at it properly. We'll now do a whole bunch of addition to this little core, and we'll do it slowly so that you understand what's happening. The result of doing this structure and its connection to the rat brain that we just saw before, they did this nice experiment, which is quantifying how high level and low level the different part of this artificial brain is compared to the rat brain. So here we have a nice rat brain over here with different region, and what this is showing is that different region will have different participation ratio. So it's a statistic that measure the effective neural dimensionality and hierarchical position across different cortical area. When you have an untrained model, both PR are the same. So of the H module and then the L module, and when you train it, then they specialize. So one is specialized into lower processing, and then another one in higher level processing. So the first thing that you might ask yourself here is, how are you going to train this? Because if you train an RNN, you know you're going to have to do some form of backpropagation through time. But now you have a backpropagation through time through different hierarchy. How does it work? So the good news is that it doesn't have to work. What they are saying in the paper is that they found an approximation, which is a one-step gradient. And the idea here is that you calculate your loss with your Y hat and the actual Y. And with this loss, you just need to hit a point where there's convergence with these two models. And it happens to be at the end of the run. So what you can do is a one-step gradient. So instead of trying to unroll it through time, you just do it at the end completely. So whatever the state was for the model here, you're doing the backpropagation at this point using that state and that other state. And then you should be good to go. So you're following this path here instead of having to waddle through all of the other arrows. So this training regimen will be used throughout the rest of the setup, even if we're adding extra stuff on top. So now we have everything. Technically, the HRM is done. It's all good. We have our recurrence, latent reasoning loops inside the model. The other decided to do something else, introducing another loop, what we're calling the outer loop of the model. This loop is extremely important and is one of the core driver of the model performance. So this the outer loop that I'm talking about look like this. You have your normal HRM in here with the one-step gradient backpropagation going on here. And effectively you have the L module state that will then currently go back to the first state, and same thing for the N H model state, and it will recurrently go back over here at the start, and then it will start the cycle again. So we're doing multiple cycle of the same stuff. So we're not adding any new parameters here. It's the same amount of parameters. So if we were to take it step by step, what we'll have is an example input like these two. Let's say this one, this is the test input. You enter here, and then after the first cycle, what would you have is this at time step 0. And after another cycle of going through the HRM, you would have something like this. And then another cycle after that, you would have this, and then third, fourth cycle, and then fifth cycle over here. So this whole cycling thing, we'll call it a segment. So after 5 segments, you will output this, and this will then be compared to the original output, which is this one. So this is all cool. So you kind of do some sort of inference time scaling so that you're doing more compute to be able to output a better answer. And to train this, what you do is what's called deep supervision. Effectively, you're going to do the following. You're going to start from a given state in one segment and then run forward pass through the HRM model. And once you're done, you're going to calculate loss with whatever you have at the moment. So you have this intermediary output. This will be your output. You're going to calculate the loss based on this. And then you're going to update the parameter. So you're going to run your Adam A102. At this intermediate step, you're going to change the parameters. You're going to reset the gradient back to 0. And then you do another cycle. So this is how you're doing this stuff in order to avoid the gradient leaking across segment. Okay, so this part is one of the most important part of the whole architecture. It's not the hierarchical component that is important, it's this thing. So we're gonna take it a bit more slowly and we're gonna unroll it so that we understand correctly what's happening at each time point. So we start at the beginning here with our test input, and then it will go into the model and it will do its stuff. It will activate these things and go like this. And then at the final stage here, we're gonna make our output, and this will be our output. This will then calculate with the loss. We're at time step 1 here, and then we'll do our 1-step gradient over here, and then flush everything out once we update these 2 model parameter, and now we're ready for another segment. So this was segment number 1, and then we iterate. Remember, like this input, it's not the partial input of the model. These are the partial input. This is still the input from the very beginning here that we're feeding back into the next segment. So we're doing the same story again. We go like this, and then here we'll look at our output, look at the actual output that we should be doing. We do a 1-step gradient and we iterate. So this was the second segment. And then you iterate like this, segment by segment, to train the model. And then at the end, let's say after 4 segments, let's say this was your maximum, you do your final output and then you're done. And you're also going to do another gradient update step and change your parameter. So in total, during this deep supervision training process, you change the parameter 4 times. So at this point, you might ask yourself, what is the correct amount of segment? Should be 4 like this, or 16, 100, what it should be? Generally speaking, the more the better. What is cool with model like this that have a self-latent reasoning loop is that you can use the intermediate output and the state of the parameter to decide if you should go further or not. And this is called adaptive computation time processing. And this model actually is able to implement it. So now we're going to take the structure and we're going to add something that will allow it to know if it should continue for another segment or should stop. So if we clean up a bit this outer loop structure, we get this. It's the same idea as before. So we have a segment over here. And then we have the H model state flowing back in at the beginning over here per segment. And same thing here with the L module state. And these run for n times t times s time. So the way to add adaptive computation time capability into this model, the other found that you could actually add element to it, which will then be able to decide if you should stop the computation or continue for another cycle. We have the following. We have a Q head, and the Q head only accepts the H module state at whatever segment it is right now. And this is what will be used to decide if you should continue or not. And this will also, if you decide to alt the computation, then the Y hat will go directly unchanged into the final Y hat. And that's the end of the run, basically. So this is great, but it's not enough to get a good performance on ARC. There's actually a whole scaffolding that you have to do, because remember, these models are not pre-trained with large amount of data. They are very small model that will work on specific kind of puzzle that they're being tested on. So now we're going to look at data augmentation infrastructure, which is a crucial component of this whole thing. So for the framework to make this model work, there's 2 things. There's the data augmentation part and the puzzle embedding. And just a refresher, ARC, what's happening is you have 2 exemplar of the task with the input and then the output. Otherwise, you will not be able to know what the heck you should be doing. And here you receive for the actual test one input. And then you have 2 tries to output the right output for this input. Now, this model is not pre-trained on anything. It doesn't know anything. It's just a 27 million parameter model that is ready to be trained and then used in this specific task. So it needs to be trained in order to be useful. So this is where the data augmentation part comes in. And then it needs puzzle embedding to have a high signal to noise ratio about what actually you need to do right now. And this, if you read the paper, you might be puzzled because it was literally one phrase that explained the puzzle embedding, and it is an important component of the system. So let's just dive a bit on it. What you have in the embedding layer actually is you have the input coming in, and then you have what's called a color embedding layer to create your actual input embedding, which has this dimension. And then you have the puzzle embedding layer, which you can think of it as a hash that tell the model exactly what it should be doing for this given input, which it was kind of trained upon previously. So this is not cheating, as we're going to see in a few. You can think of this as a very high signal about what exactly it should be trying to do now in its system. So that being said, the whole architecture looked like this, like we saw at the beginning. And it starts first and foremost with data augmentation. So you get your input that we discussed. And since you know the input and output pairing for, yes, a few of them, the first thing you're going to do is you're actually going to make a whole lot more. So you're going to make translation, rotation, flips, and color permutation in order to create a data set which you're going to be able to train on right now. And for this specific model, 300 to 1,000 example is good enough, with 300 being the sweet spot in terms of computation versus performance. So you say you have your 300 example, then what happened is that you technically have 300 example of elements that are transformed. So it's not the actual stuff. And you have the hash for this transformation that will be then fed into the puzzle embedding layer so that the model knows that this was a transformation and it was a transformation like this. And here's my input. And then you will try to output the element, but in the transformed state. So once it's in the transformed state, it will never be right because it is transformed. So what you have to do actually in order to make a proper output is you have to take the transformation recipe, invert it, you flip it back, and then you create your data set of 300 to 1,000 output pairs, which are the final add, but now reversed. So once you have that reversed transform data set of output, the model will then run a scan in order to figure out which one of these configurations appear the most. And the top 2 will then be your output. And that's how it works.
Undoubtedly, the HRM architecture is very interesting at the very least, but does it work? Does it deliver on its promise?
Remember, the Sudoku puzzle belongs to a class of problems that surface the Achilles heel of the transformer, that it's not computationally universal. In this plot, which shows Sudoku accuracy against the number of layers in the model, the standard transformer plateaus around 60% accuracy. Even adding more layers doesn't help beyond a certain point. It turns out, its effective computational depth is far shallower than the number of layers. In contrast, HRM reaches near perfect accuracy.
These results look impressive, but I do have a problem with the dataset. The fact that it was published in the same paper as the model. Normally, benchmarks get their own paper so that the community gets the chance to poke holes and make sure the dataset is robust to issues like training data leakage. When you evaluate your fresh model on a fresh dataset, you jeopardize your credibility a little bit.
One of the main reasons why this paper made headlines is its performance on the ARC-AGI leaderboard. ARC-AGI stands for Abstract Reasoning Corpus for Artificial General Intelligence, but the key part is reasoning. Here's one sample task. During inference, the model is given a few examples that solve an unspecified task and is then challenged to solve a new example. The task here is obvious to humans. Close the fuchsia L shapes with a yellow square. But for an LLM, it might not be obvious what it's being asked to do. This data pattern doesn't match the free-form text it was trained on, so it would have to exhibit inductive reasoning instead. Despite being published back in 2019, the ARC-AGI leaderboard hasn't yet been saturated. While humans scored 98%, it took 5 years until GPT-4o scored for the first time above 0. This last year has seen a lot of progress, though. OpenAI's O3 model achieves 75%, and the Grok 4 runner-up scores over 66%. HRM fits right in the middle of this leaderboard, somewhere in between O3 Mini High and Claude 3.7. A middle position might not sound very impressive at first, but remember, this is a 27 million parameter model, about 20 times smaller than its neighbors. Now, there was a little bit of Twitter drama here. Initially, the creators of ARC accused HRM of cheating, but then deleted the post. The issue is, HRM took the sample pairs from the evaluation set, augmented them into 1,000 variants through operations like rotations, and then added them to the training set. On top of this, they trained task embeddings. So, when presented with the challenge at inference time, the model is already aware that it's expected to fill the shapes with a yellow square. This might technically obey the ARC rules, but definitely not its spirit. ARC was designed to test inductive reasoning on completely new tasks.
Personally, I think this whole discussion around ARC-AGI is a moot point. It's just not fair to compare fully fledged general-purpose LLMs against the model that was trained for ARC-AGI and only on ARC-AGI. Remember, HRM is not an LLM. It doesn't produce text, and you can't chat with it, so it's just not an apples-to-apples comparison.
Here's a better point of reference. The ARC organization tried to reproduce the results in the HRM paper and compared it against a vanilla transformer with the same size, that is, 27 million parameters. In this context, the regular transformer does underperform HRM, but by less than 5 percentage points, and the gap closes as the number of outer loops increases.
Zooming out, my take on the evaluation section is that HRM passes some sort of unit test. It scores non-zero on a admittedly difficult benchmark, and that justifies scaling it up and attempting to turn it into a fully fledged LLM.
What do you think about the paper?
Chain of thought is a hack, in one way or another going to get replaced by some form of recurrence.
When I saw the brain, I was sold. Like the first page, there's a brain in there.
I think the spirit of the paper will live on.
I think it's already living on. The idea of bringing the reasoning loop